Okay, so then today's lecture is going to be about voting and the mathematical theory of social choice. It's actually an interesting application of analysis of Boolean functions, and in fact, it's a good way to motivate a lot of the basic definitions. One of which is the definition of influences, which we'll talk a lot about today. Okay, so when you think about voting, especially these days with the American presidential election coming up so soon, you may mainly probably think about elections for president and things, but it's actually a broader area than that. You should also keep in mind examples like committee just trying to decide on which of a bunch of options to take, or in computer science, like if you have maybe a search engine aggregator, you might get results from different search engines and sort of let them vote on what the best outcome is. So it comes up even in not just the real social choice of the world, but let's say, for example, in artificial intelligence a lot. In particular, our best friend for the class, the Boolean function, can be very well thought of as a voting rule in an election with n voters and 2 candidates. Okay, so the voters correspond to the input coordinates, and the 2 candidates are named, let's say, plus or minus 1. Okay, so if everybody votes, that gives you a list of n plus or minus 1s, to which you can apply f, which gives you an outcome. And you think of that as the winner of the election given the votes. Okay, and you can imagine different voting rules. For example, probably the most natural voting rule of all is majority vote. That's the most familiar one. So it's a very important Boolean function, which I denote as majority sub n. So given the list of n votes, you just output the more common vote. Okay, and there's actually an elegant, simple formula you can write for that, given that we're using plus or minus 1 notation. It's just the sign of the sum of the votes. Okay. And I'm always going to assume that n is odd, because I don't want to worry about ties. It's just more elegant if you just take n to be odd always. Okay, but maybe that's the election scheme that you would suggest if you were actually designing an election, but it's not the one that's always used. For example, that's not the scheme by which, let's say, the American president will be elected. I guess it was the scheme by which the Mexican president was recently elected, ignoring the fact that they have essentially 2 main parties. But it's actually one of the very, very rare countries where the president is just elected by direct plurality vote. Hard to find examples of that. But not only do other systems get used in practice, it'd be also natural to use other systems sometimes. For example, if you're having a committee to decide on something, sometimes it's important that you only pass, let's say, a resolution if everybody agrees, if it's unanimous. Okay, so that would correspond to another very popular pair of Boolean functions, the AND function. It's the logical AND function, let's say, which in our notation is true if x is all trues, or false if somebody votes for false. Okay, and the OR function is the Boolean dual of this, which is true unless all the inputs are false. Okay, so that's another popular Boolean function. Another voting rule that you may often encounter in practice, let's say in North Sudan, is a dictator voting scheme. And this is the one where there's one person, and their vote is the only one that matters. Okay, so they directly elect the winner, let's say themselves. Yeah, so our notation for that will actually be chi sub I. We can use a notation we already have. It's, I guess you could call it the parity of all of the coordinates in the set. Let me write the set I, just the singleton set I. Okay, so this is just xi. Everybody votes, and then whatever the ith person says is the outcome. Okay, so that's like a very simple, like a ridiculously simple function. We're also going to use the notation chi I here. And it seems a bit like melodramatic to give it the name like dictator when it's just, I don't know, the ith coordinate function or the ith projection function. But actually, hard it is to imagine. These are very important functions in analysis of Boolean functions, and it's actually very handy to have a name for them. So these will be what we call them, the dictator functions. Okay, great. So along that lines of rather disappointingly unfair election schemes, Let me give you another important function that has kind of a melodramatic name, but it's a very important concept in analysis of Boolean functions. OK, so we say that K-hun is a Boolean function that depends on at most k of the input coordinates. Okay, so even though it's potentially defined on n input bits or the n people voting, there's some at most k coordinates such that the outcome is entirely determined by what goes in there. Okay, so for example, this is a 1 junta. And generally, we kind of imagine in our heads like k is like a constant independent of n. OK, so this is another kind of voting system you see in practice. I guess this term comes from the junta that was in place in Chile in the 70s, I think. I also learned that Fiji is apparently currently a junta. They're led by a military junta, so it exists even today. OK, just to make sure you're on top of the notation, let me ask you a question. How many 1 juntas are there? Keep going.
2n plus 2?
Who said 2n plus 2? Marla, yes. OK, so the answer was 2n plus 2. The plus 2 is for the two constant functions, which don't depend on any input coordinates. They're 0 juntas. And then the first n is for the n dictators. And the other n is for the n anti-dictators, or negated dictators. F of x equals minus xi. That's a voting scheme rarely seen in practice. OK. Actually, one that's plausible and one does see in practice. For example, the EU's Council of Ministers is an example of a political body that uses a voting rule like this, is the weighted majority function. OK, so a weighted majority function is similar to a majority. It's just that like some parties or voters get more like points than the other ones. OK, perhaps as in the case of the EU, it's because some countries have a bigger population than others. OK, so a weighted majority OK, also sometimes known as a linear threshold function. Is any function representable like this, only with weights? Is any f representable as f of x equals the sine of some linear over the reals function? So a0 plus a1 x1 plus dot 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 plus an xn, where these AIs are reals. OK, so most likely you would think of the AIs also as being positive, so that your vote is like positively correlated with the outcome, but we allow the opposite too. OK, so again, just to check the definitions of these four functions, majority, and, or, and dictator, which ones are weighted majorities? Yeah, that's right, all of them. Yeah, so majority obviously is, and also is, basically because you imagine you sum up all of the inputs, and then you have to maybe add n or n plus or minus a half or something to sort of shift the threshold, just so that you get overall this quantity is negative if all of the xi's are minus 1, and it's positive if at least one is minus 1. OK, and a dictator is also a weighted majority, just where all the AIs are 0 except for the ith AI is 1, or any positive number. OK? Yeah, since it's the season for the US presidential election, yeah, so the president of the United States, it kind of gets elected in a funny way. Like, if there are n voters, they're broken up into these blocks corresponding to like states plus DC. So there's like 51 blocks. of differing sizes, and then sort of on each block you take the majority. Okay, that's not majority of n, it's some majority. And then overall, the winner is like some weighted majority, where each state gets something like 2 plus a number which is proportional to its population, kind of. Okay, so that's some kind of weirdo scheme for, this is assuming 2 parties. This is the Electoral College scheme that is used to elect a president.
I mean, not every state is required to use a majority voting scheme.
Ooh. Technically, yeah. Also, not every. There's a couple of states where it can, like, it can allocate its electors.
It doesn't matter because you can just, like, use parts of states instead of whole states.
Yeah, I think a couple of states, yeah, like they look at the proportion of voters that vote for each party and they allocate them.
The way that Nebraska works,
Oh, is it county-wise?
no, the way that Nebraska works is
I see.
there's two senators and 3 representatives, right?
Right.
The 2 senators, so we get 5 votes. So the 2 votes that correspond to the senators are just statewide majority.
Statewise, and the other ones are congressional district-wise. I see. Yeah, so there you'd have to do like you'd have to do like 2 different functions, like based on that block. Are you from Nebraska?
Yeah.
I see.
I think there are also some states that aren't required to do things by majority, even like.
Oh,
I think that some states
it's just custom that the electors will go with them. Yeah. Yeah.
Right. No state is required, but some states' constitutions do not dictate this.
I see.
Yeah.
Okay, so for example, in Canada, where I'm from, there actually are rules, but it's similar to this in the sense that if there were 2 parties, which there aren't, but if there were, then it would go by breaking them up into unequal sized blocks, these ridings, which is like a district. And you sort of like locally take the majority on each one of those, and then the majority overall gets to decide the prime minister.
Where in Canada?
I'll tell you later. Yeah. No. Okay. So that's that one. Let me mention one more, which these are actually, come up in real life. This one more like comes up in analysis of Boolean functions, but it's important. Let me draw it on this board. This is an interesting example of a Boolean function. It's really just a read once DNF if you're into concrete complexity. But it was cooked up by Ben Orr and Lineal in 1985 to be an interesting example or counterexample function. I'll say more about that later. It's called the tribes function, and it takes 2 parameters, w and s. And it's defined on w times s many bits. And it's sort of a similar picture. So you break up the n voters into blocks, each of size w. So far, it's similar. And then on each of these, you take an and. And then overall, you take an or. And there are S blocks. Okay, so it's like, they call the tribes, they're like each one of these is a tribe, and overall, the outcome is true if at least one tribe is unanimously in favor of true. Okay, so I don't know if that would occur in practice, but it'll be an interesting function for us. Okay, so one thing we're going to kind of do today is talk about comparing these different rules. I don't know, to see what properties they have or see which one is better than another or whatnot, mathematically. So in some sense, it's a little bogus because for 2-party elections, for almost any, like, I don't know, criteria you could think of that reasonably approximates like fairness, majority will be the best rule. Which is nice for democracy. Although things get much more complicated, as you may know if you study social choice, if there are more than 2 parties. But we're just going to stick to 2 parties and nevertheless talk about various properties of voting rules. So here are some basic properties that you might think a reasonable voting rule should have. Okay, and these are also nice properties of Boolean functions. So one is, this is really a bunch of definitions. It can be monotone, okay, which is sometimes called positively responsive in the social choice literature. And that just means that f of x well, it's what you'd think, is less than or equal to f of y whenever x is less than or equal to y pointwise. Or another way to think about it is if you take some votes, and let's say the outcome is plus, and then you change somebody's vote from minus to plus, it can never make the outcome go back to minus. So if you change somebody's vote, that can only cause the outcome to change in their favor, not the reverse. OK, that's a natural property for a voting scheme to have. Here's another one. You saw it on the homework. The property of being odd, or it's sometimes called neutral in social choice. And as you saw in the homework, this is just f of minus x equals minus f of x. Okay, so if everybody reverses their vote, then the outcome of the election is reversed. Or in other words, the voting rule doesn't depend on the names of the parties, plus or minus 1. If you reverse the sense of plus or minus 1, it would be the same. Okay. Another natural one is a Boolean function can be symmetric. Okay. In the voting literature, this is also called anonymous. And that essentially means that the rule doesn't depend on the identities of the voters. So it's totally symmetric with respect to the coordinates. In other words, I'll invent some notation, which I hope you'll guess the meaning of. F of x permuted by pi, this is some permutation on the coordinates, permutation of n symbols, is the same as f of x for all x. Sorry, this is, yeah, for all pi and also for all x. Okay? Correct. The tribes does not have that property, although I will come back to that in a second. Because it's pretty symmetric in the sense that if I said, you know, we're going to go for a tribes voting scheme, Marla, which of the n voters would you like to be? You would say, it doesn't matter to me. They're all the same. But it's not actually fully symmetric. So it has a weaker property that I'll mention in a second. What else? One more property that comes up in Arrow's theorem, which is something we'll prove next time, is function can be unanimous or Paretian. If everybody votes the same way, then that's the outcome. Okay, that's a simple property. And these are actually perfectly interesting properties to study for any Boolean function, even into the reals. Let me add one more property here. Unbiased, we defined this on day 1. This just means that the expectation over a random x of f of x is 0. Meaning that in its outputs, there are equally many pluses or minuses, which also seems like a fair property.
Isn't that covered by odd?
So yeah, that's a good point. Any odd function is unbiased, but not necessarily the reverse. Good. OK, so let's just make a big chart so that we can look at all the functions that we saw before. And we'll mark down which of them have which properties, and that'll help us explore the properties a little bit. So let me use a different color. This giant chart. OK, so the functions I'll look at are majority and, or also or. They'll have sort of the same properties. Dictator. This Electoral College thing used in the United States, and tribes. OK, so in fact, since I have it here, it's going to be monotone, odd, symmetric, unanimous, let's say unbiased. OK, so let's do majority. As I said, majority is super nice, so I think it's going to have all of the properties. OK. So let me put a check mark in there. If you don't see it, in the majority, if I change my vote from minus to plus, it can only make the outcome plus. Switching all the votes switches the outcome. It's totally symmetric. It's unanimous. It's unbiased. In particular, it's odd. So majority looks pretty great. Okay, so how about this one? And just shout them out. Is it monotone? Yes. Is it odd? No. It's definitely not symmetric with respect to the names of the candidates, true and false. Symmetric? Yeah. Yep. And unanimous? Yeah. Yep. And it's not unbiased. Okay. Dictator? Monotone? Yep. Yep. Odd? Yep. If the dictator reverses the vote, the outcome reverses. Symmetric? Okay, that's a big no. Unanimous? Yep. And unbiased? Well, yes, it's odd. All right. Electoral College, monotone? Let's say under this formulation. Yeah, it's got that going for it at least. It's monotone. Odd? Yeah, it is odd. Yep. Because if you flip all the votes, each of the majorities will flip, and that's like flipping all of the votes into this weighted majority. If you think about a weighted majority, oh, not true. Yeah, the weighted majority might itself be biased. For example, this could be and, right? We know and is a weighted majority, and it's not odd if you flip the outcome or the votes. If it doesn't necessarily flip the outcome. So if this were majority on top, or some weighted threshold function that didn't have an A0, then that would be a check mark. Okay, so majority of majorities is odd, but this guy could be biased towards plus or towards minus. Okay, symmetric.
No, but it's still.
Not in the US, that's true. In the US, there is no constant term, so yeah, yes in the US. I guess in most versions of Electoral College. Yeah. Okay, so yeah, perhaps yes. Okay, symmetric, no, because the states have different sizes, so your vote may be worth more or less than one of them. Unanimous, yes, and unbiased, kind of depends, right? Actually, again, if it were a straight majority of majorities, or another weighted majority without constant terms, then it would be unbiased. So actually, yes in the US. Okay, and finally, tribes. Tribes is monotone. And it's not odd, because there is an asymmetry between plus or minus. It could be that like none of the tribes is unanimous, but it's not anti-unanimous either. So then flipping all the votes in that situation would not flip the outcome. So it's not symmetric, but this is a point, yeah, I want to address. It is unanimous. And whether or not it's unbiased actually depends on W and S. But let me say one thing here, which I'll use in a second. There is a setting for like S and W such that it's essentially almost unbiased. Because you see, the probability, if I were to choose a random x, that a true would come out of here is something like, well, it is 2 to the minus w. So if S is somehow close to 2 to the w, then it could be close to unbiased. In particular, let me just say, if S is approximately ln 2 times 2 to the w, then it's, let's say, approximately unbiased. This is not an integer, so you can't make it exactly unbiased. But you can actually make it pretty close if you set the parameters appropriately. OK, so now let me return to this issue about tribes, which, looking at it, you see it has some kind of symmetry property. OK, and that symmetry property I call transitive symmetry. So if you know some group theory, that's where the word transitive is coming from. But if you don't, never mind. So formally, you say that a voting rule or Boolean function f is transitive symmetric. This is a weaker condition than being symmetric. If for every pair of voters, I and I prime. There is a permutation of the voters which maps I to I prime and which the function is symmetric under. So what I mean is there exists a permutation pi in Sn such that pi maps I to I prime and f of x permuted by pi equals f of x for all x. Okay, which sort of captures the idea that any voter is like any other voter if you fix those two voters in advance. Okay, so in the case of tribes, if I and I prime are both inside the same tribe, then you can just permute, just switch these two voters. Okay, and the tribes function doesn't change if you switch these two voters. Because it really just matters if they vote both 1 when the other guys are voting 1. Or minus 1, I guess. And if I and I prime are in different tribes, then you can switch these two tribes and also switch the voters inside the tribe to make them match up. Okay.
So this doesn't necessarily require that you're actually switching I and I. It just means that you're taking I to I prime split go forever, right?
Yes. Yeah. So in particular, like, if I and I prime are in different tribes, you can't just switch I and I prime. But you can switch the whole tribe, so the other voters in this tribe will move to this tribe. Okay, this maybe the formal definition takes a little thinking about, but the general idea is that if you fix any two voters, they kind of act the same, or you wouldn't rather be one or the other. Okay, any questions about that? Okay. All right, so now that we've made all these nice definitions, we can talk a little bit more about comparing voting schemes. And to do this, we're actually going to make an assumption about how people vote, which looks a little crazy, but I'll try to justify it a little. In fact, it's an assumption we already sort of implicitly made when we defined the notion of an unbiased function. Still faintly up here. It involved imagining the scenario when the votes were uniformly random. Okay, so in social choice, this assumption is called the impartial culture assumption for some reason. So it's a hypothesis that they work with sometimes. And it just means that the votes are uniformly and random and independent. Okay, and this was introduced by two people, Garmin and Kamian, who are at Tepper working on these issues in 1968. And it looks a little ridiculous because, I mean, that's not probably the best model of how people actually vote. But I would say it's a good model, like, to compare voting rules in the absence of, like, any other information, just, like, totally abstractly or hypothetically. And you might imagine, I don't know, more realistically that maybe in some elections there are some partisan voters who are just essentially always going to vote the same way, and you can, like, factor them into the function as a constant. And then perhaps the remaining voters could be thought of as, the potential swing voters as voting randomly. Okay, it's not the greatest model, but as I said, it's good for comparing voting schemes in the abstract. Okay, and it's a known concept in social choice. Okay, I don't have to defend it too much because this class really isn't about social choice. It's about Boolean functions. So there, it's also a nice assumption. Okay, so great. So having defined all these things, let's go to the question of whether or not your vote makes a difference. Okay, and that leads us to this definition of the influence of a voter on an election. Okay, so giving a voting rule, we define the influence of voter I on a Boolean valued function f to be, basically, it's the probability under the impartial culture assumption that your vote is like a swing vote, in the sense that if you had reversed your vote, it would have reversed the outcome of the whole election. So it's the probability over x chosen uniformly at random that f of x, the actual outcome of the election, is different from what it would be if the ith voter had reversed their vote. Okay, so here I invented some notation, x superscript parity I. This means x1 through xi minus 1, but then you reverse xi. Okay? That's the fraction of the time over everybody else's votes that you make the difference. Okay, this was invented actually independently by several people. One was a geneticist in England in 1946 called Penrose. I'm not sure why he was thinking about it. And then it was later invented by a lawyer called Banzoff in America in 1967. Sort of famous for other legal reasons. But he invented this for one lawsuit he was working on, which you can read about in the homework. And for that reason, actually, it's sometimes called the Banzoff power index. Okay, so this is sometimes called the Banzoff index. It was also later invented again independently by Coleman, who was working on social choice. So I guess that means it's a natural definition. Okay, so it kind of measures a voter's power or influence. So let's do some examples just so we all see the definition. So how about in the AND election, if we're using the AND of the votes, what is the influence of, let's say, the ith voter? Nope.
It's only going to make a difference if everyone else is voting one.
Right, that's right. So the observation is, let's say you're the ith voter, your vote actually affects the outcome if and only if everybody else votes for true. Right? Because if everybody else isn't unanimous, then your vote doesn't matter. Conversely, if everybody else is unanimously in favor of true, your vote does matter. So therefore, it's 2 to the minus n minus 1. Okay, that's the probability that everybody else will be voting for true. Okay, so that's very small. That's the same influence, actually, for all I. Okay. What about, here's another voting scheme, the dictator scheme. Okay, in the ith dictator scheme, what is the influence of the ith coordinate? I see a 1. Yeah, it's 1. Because that person, if they reverse their vote, it always makes a difference. Okay, and this is the maximum. Okay, so influences are between 0 and 1. They're probabilities. That's the biggest possible. Okay, and I guess you also probably clearly see that the influence of voter I on some dictator that is not I is 0. Their vote has no effect. Okay, how about, okay, this is an election scheme that I'm sure, or I hope, has never been used in practice. The parity of all the votes. So this is the scheme that you take the winner is true if an odd number of people vote for true. But it's a Boolean function, so.
So this is used, right?
Is it?
If two people are trying to choose something, you hold out a number of, you decide who's odd and who's even, and you throw out a number of fingers.
Oh, yeah. That's true. Yeah, it is used in those two-player games with odd and even. Okay, good. Great.
I used this to figure out whether my roommate or I got the bigger room in our house. We decided whether the outcome of the Patriots game was going to be odd or even the sum of the scores.
Oh, nice. Okay, there you go. All right, great. So it's legitimately for me to ask you then. What is the influence of a voter on this scheme? Whoever said 1 was correct, yeah. Because if you're taking the parity of all the bits, then regardless of how everybody votes, if you flip your vote, that flips the outcome of the election. And let's do the most interesting example, which is the influence of the ith voter on the majority scheme. Okay? So if we're actually voting according to majority, under what circumstance does my vote make the difference with respect to the other people's votes? Yeah, if everybody else votes exactly split, half-half. That's exactly the scenario in which my vote makes a difference. Okay, and that occurs with probability. Well, it's like you toss n minus 1 coins, and you're looking for the probability that you get exactly n minus 1 over 2 heads. So it's this over 2 to the n.
N minus 1.
Yeah, over n minus 1. Okay, and does somebody know the asymptotics of that?
1 over root n.
Yeah, it's like it's a fact. If you don't know, it's something like constant over root n. In fact, the constant is, I'll tell it to you for fun. It's asymptotic to root 2 over pi over root n. Okay, you can forget about the constant. I put it in just for fun. It's something like constant over root n. Okay, and that's actually very small. I mean, it goes to 0 as n goes to infinity. So for a large election, your influence under this definition is negligible. Okay, is that clear? Okay. Actually, that leads to like a slightly interesting question, which is, this is a voting scheme majority where everybody has very small influence, 1 over root n. Now, I guess here's another example of that happening, the AND scheme. Everybody has tiny influence. But the AND scheme is a little bit unfair because it's practically the constant function. Okay, so it's not really that fair to ask about the probability that your vote changes the outcome, since the thing is almost constant. But if, let's say, you restrict to unbiased functions, those are the 50-50, true or false, then it's interesting to ask, among those kinds of election schemes, could it be that everybody's influence is even smaller than this? Since majority is such an interesting and nice and symmetric function, you might guess that the answer is no, that somehow it has the minimum maximum influences. But that's actually not true at all. So it turns out, I'm not going to do this calculation, and I also took it off the homework, but it turns out that in the tribes function, this guy right here, everybody has the same influence because it's transitive symmetric, so everybody's kind of the same. And if you pick these parameters, s and w, exactly as I said before, where s is roughly ln 2 to the w, such that it's roughly unbiased. Okay, in this case, n is s times w. That's the number of total voters. Then it turns out if you do a little calculation, it's not very hard. This is asymptotic to ln n over n for all I. So that's actually much smaller. It's almost 1 over n. It's ln n over n. So somehow, I can't exactly explain it per se, but it's an election scheme where, like, despite the fact that it's unbiased, everybody has extremely low influence on the outcome.
So here the width w is roughly log n?
Yes. Here the width is roughly log n, and s is roughly n over log n. Yeah, so somehow to be influential here, you can do this calculation in the back of your head if you get bored. To be influential in this scheme, everybody else in your tribe has to vote for true. And furthermore, actually, everybody outside all of these tribes have to not be unanimously in favor of true. But already you see it's something like 2 to the minus w. It does, yeah. It sort of shares the same flavor of and, yet manages to be essentially balanced. That's kind of cool. So in fact, yeah, this was noticed by the namers of the tribes, Benor and Lineal, back in 1985. They're actually working on some problem in distributed computing where these issues were important. The eraser is horrible. And they conjectured that actually it was sort of the worst. That you couldn't have like an unbiased function where all the influences were even lower than that. And we're going to talk about that a little later and also in the homework. But that conjecture was resolved in '88 in this famous theorem by Kahn, Colley, and Lineal, which I mentioned in lecture 1, it's kind of like the watershed theorem in analysis of Boolean functions that really showed the range of mathematics that could be used to study Boolean functions, and also gave like this very impressive result. And it essentially says that indeed this is optimal or pessimal. So it shows that if f is any Boolean function, then there exists a voter whose influence is at least, well, ln n over n. So omega means up to a constant. So far it's false because there's this example, but times the variance of f. Okay, and if you remember, the variance is like a number that kind of measures how close a function is to being constant. And this thing is 1 if f is unbiased. For example, if f is plus 1 with probability p, where p is small, then this is roughly proportional to p. So it actually covers a lot of cases. In particular, if you're unbiased or even nearly unbiased, you must have an influence that's at least ln n over n. That's Gilkali. That's a great theorem. It has some implication in social choice, too. Like in this impartial culture model, it implies that for any election scheme at all, there's always some little o of 1 subset of the voters, such that if you bribe the voters in your favor, then you'll almost surely fix the outcome of the election in your favor. And it looks like a simple statement, and it looks like combinatorial, but as we'll see eventually when we prove this, like the only way known how to prove this is very analytical and relies on a powerful theorem about Boolean random variables. Yeah.
There's still a gap between this and Tribe, right? So Tribe, every variable has influence, but KKL says there's just this one. Is there something started at this there are many?
Yes, that's a good question. The question, this only guarantees you that you have a 1 influence that's large, whereas in tribes they're all that large. There are stronger versions. See if I can write one that's correct off the top of my head. Talleyrand showed later something like, for any Boolean function, the sum over I goes from 1 to n. I don't know if I can get this. The influence of I on f over log 1 over the influence of I on f is at least some constant times the variance. I think that's right. And somehow this shows that, well, it's a stronger statement that is towards showing that like lots of them are large. I'll double check that though. Okay. Great. So now that's very combinatorial, this notion of influence. But, well, as I alluded to regarding the proof of the KKL theorem, you need to get a little analytic to prove it, even though it's a combinatorial-looking statement. And that's going to actually motivate us to define influences even for functions whose range is the real numbers. So we'll need a different definition. And for that definition, first we're going to define something called the derivative operator. So the ith derivative operator, denoted d sub I, is an operator on Boolean functions, on this vector space of functions from the hypercube into the reals. So a linear operator maps the function f into another function called d sub I of f via the following definition. To evaluate d sub I of f, the ith derivative, at x, first you do f of x, but you fix, this is some invented notation as well, you fix the ith coordinate of x to be plus 1. You subtract the value when you fix the ith coordinate to be minus 1, and you divide by 2. Okay, so this thing means x1 through xi minus 1 plus 1 xi plus 1 xn. Let me make a comment here. Although this function is defined on n input coordinates, it actually does not depend on the value of the ith coordinate of x. It does not depend on xi. Because it doesn't matter, you're just always changing the value. So it doesn't matter, but nevertheless, we'll think about it as a function on all n coordinates. OK, so that looks a bit abstract, but let me try to explain it somewhat and explain why it's called the derivative. So first, let's see what this means in our most favorite case when f is a function into plus or minus 1. So if f happens to map into plus or minus 1, then it has more of a meaning. DIF of x equals, well, the point is that it's 0 if changing the ith bit doesn't matter on that value of x. So it's 0 if, let me write, coordinate I is not pivotal on x. Or in the election terms, if voter's i's vote doesn't make a difference given everybody else's votes. Okay? And otherwise, if it does make a difference, you're either doing 1 minus minus 1 over 2, which is 1, or the negation of that, which is minus 1. So let me just say it's plus or minus 1 if coordinate I is pivotal. OK? In particular, knowing that, if we were to square this function, DIF of x squared, that would give us the 0, 1 indicator that I is pivotal on x.
The expectation is DIF of x squared is then just the amount divided, or sorry, not amount divided, influence, there we go.
Exactly. So the influence of I on f in this case is just the expectation of this. OK, so that's another way to write the influence. And this is what we're going to take as our definition of the influence of a general function. OK, so what I'm saying here is this is a generalization of our earlier definition. If you have a real valued function, we define the influence like with this formula. OK, so it's non-negative, for example, but it's not necessarily at most 1. OK. By the way, this is just the expectation of the square of a function. In our, if you remember this notation, it's like the correlation of this function with itself. OK, that's a definition of this inner product on functions, or we would even write this as the 2 norm of the function squared. OK. Now what I want to show you is that there's a good reason why this thing is called the derivative operator. One reason, which you can check for yourself, it's straight from the definition, is that f is monotone if and only if this function di of f is non-negative for all x and I. Okay, so it's just like in calculus, like a function is monotone increasing if its derivative is always non-negative. But that's not the real reason we call it the derivative. The real reason we call it the derivative is as follows. So here's a little, I'll call it a theorem. Let f of x be any Boolean function into the reals. Okay, so we know it has a Fourier expansion, which is just writing it as a multilinear polynomial. So it looks like this. Okay. And what I want to tell you then is that if you look at DIF, that's also a function mapping the hypercube into the reals. So it has a Fourier expansion. And I will tell you its Fourier expansion. It's just what you would get if you looked at that as like a polynomial on x's and took the derivative with respect to xi, as though you were doing calculus. Which means that any monomial that does not involve xi drops out. And any monomial that does involve xi, you like erase xi from it. So you get the sum over all sets S that contain I of f hat S, and then the monomial S with I taken away. And that's the Fourier expansion of the derivative of f. Okay, this is pretty easy to prove. You just write down the definitions and it comes out. I'm going to give like a slightly slick-looking proof because I want to use a similar proof later. So it's going to look a little overkill, but let me do it anyway. So the first thing I'm going to observe is that this operator, di, is a linear operator. Meaning that di of f plus g is dif plus dig. Okay, this means you add up the functions pointwise. And why is that? Well, if you just looked at writing like plus g into this definition, this would be the derivative of f plus g. And then you could just separate it out into two fractions, the one that had f and the one that had g. So that's from the definition. I guess we should also check that di of a constant times a function is equal to the constant times dif. That's just because if you stuck a c out here, you could just factor it out. Any question about that? So good. So that means if this is f of x, it's the sum of a bunch of smaller functions, each of these monomials. So you can take its derivative by just taking the derivative of each little piece. So therefore, it suffices to check, actually, that di of each of these monomials, x of s, is what I claimed. It's x with the ith guy taken away if I is in S, and it's 0 if I is not in S. Do you see that? Why it suffices to show this? And then that's easy. If I is in S, not in S, so I don't know, maybe it's like x1, x2, x5, S is 1, 2, 5, and I is 4, then if you change I to plus or minus 1, it doesn't make a difference. So you're subtracting the same things, and you get 0. And if I were like 2 here, then when you take the derivative according to this formula, you get like x1 times 1 times x5 minus x1 times negative 1 times x5 over 2. So you indeed get x1, x5. Okay, that was a horrible proof by scribbly example, but I hope you buy it. Okay, so that's great. It means that if you have a function and you have its Fourier expansion, taking the derivative is easy. Great. So
I guess one could also see that it's a derivative by just extending the minus 1 to the n function to the cube minus 1, and then the multiplier extension of f would happen to be
Yes, but then why is it obvious that the derivative of the multilinear expansion satisfies this property?
Along the line.
Oh, because along a line, right, if you literally took the derivatives, then all the differences along the line divided by the widths would equal this, which is like the derivative when the width is 2 by linearity, multilinearity. Good, yeah, that's right. Okay, great. So now that's good because we know that if you know the Fourier expansion of a function, you can calculate its 2 norm straight from the Fourier coefficients via Parseval. Right? Parseval, if you recall, tells you that the sum of the squares of the Fourier coefficients is equal to the expectation of the square of the function. So as an immediate corollary, we get for any function f, even into the reals, we get that the influence of the ith coordinate on f is equal to the sum of the squares of the Fourier coefficients in this expansion. So it's just the sum of the squares of all the Fourier coefficients on sets that contain I. So this is a formula. And it's kind of nice because, before we called this sort of the weight of the Fourier weight of f on the set S. And this is like saying the influence of a coordinate I is like all the Fourier weights on sets that contain I. So it didn't have to work out this way, but somehow it corresponds to our idea that it measures the power of I, or the relevance of I for the function. OK, so for example, let's just double check. Remember from class 1, if you look at the majority on 3 bits, it had this expansion. A half x1 plus a half x2 plus a half x3 minus a half x1, x2, x3. And so you see that the influence of the first coordinate on majority of 3, so you just square all the Fourier coefficients, of which there are 2, that involve x1. And indeed, if you think about it, the influence of the first voter in the scheme is a half, because your vote is relevant if and only if voters 2 and 3 vote the same way. OK. So that's the formula for the influence of a coordinate on a function. Now I'll tell you another one, which is a great formula if your function happens to be monotone and a Boolean function. So this is especially relevant for voting rules because they tend to be monotone. And it says that in this case, there's a much simpler formula, Fourier formula. The ith influence is just equal to one of the Fourier coefficients, namely the one on the singleton set I, which I'm going to start writing as just f hat I. And that actually jives with this. Majority is monotone, and it's telling us, or claiming, that the influence on the first coordinate is also just this number, which is correct. So let me show you the proof of that. It's quite simple. So the point is, before we saw that for a Boolean valued function, this was sort of the plus or minus 1 indicator that voter I was pivotal given the votes x. It was 0 when it wasn't pivotal, but then it was either plus or minus 1 if it were pivotal. But when the function is monotone, it's always 1. So what I'm saying, if you look at the definition, is that in the monotone case, this thing is 0 if I is not pivotal on x. But it's always plus 1 if I is pivotal. Because for monotone functions, it'll always be that this guy is 1 and this guy is minus 1. So then you don't have to take the square anymore. You can just take the expectation. Oops. On f, it's just the expectation of the derivative. And there's a really simple formula for the expectation of a function in terms of its Fourier coefficients. It's just the empty Fourier coefficient. And what's the empty Fourier coefficient of the derivative? Well, I erased it from this board, but to take the derivative, you take the derivative. So what you'll get when you take the derivative with respect to xi, the constant term you'll get will be whatever you had on f hat, whatever you had on the singleton monomial xi before. Does that make sense? Okay. Great. Okay. So these are going to be some important formulas and notions for us when studying Boolean functions. Let me do like a quick little application of this regarding voting. So here's a little theorem. Let f be a voting rule which is monotone, which is a pretty reasonable assumption for a voting rule, and also transitive symmetric, which is also a pretty reasonable voting rule for a reasonable property for a voting scheme. Okay, if it's not completely symmetric, it should be kind of maybe be like Electoral College, which is, or tribes, which is sort of symmetric. Then all of the influences are small. Okay, so in this case, no voter has much power. Okay, so the proof of this just uses a few observations. First of all, if its function is transitive symmetric, intuitively this kind of means that all the coordinates are sort of the same. And that implies that all of the degree 1 Fourier coefficients are the same. Okay? I won't completely prove that. Maybe I'll leave it as an exercise. But if any pair of coordinates are the same under some symmetry, then you can use it to show that the singleton Fourier coefficients are the same. Okay, so all of these numbers are equal to the same number. Let's call it f hat 1. Okay, so then the influence of the ith voter, this is equal to f hat of the singleton set I by monotonicity. That's the result we just did on that pane. And that equals to f hat 1. So all of the influences equal this one Fourier coefficient. And now I'm going to use Parseval. Parseval tells me that for a Boolean valued function, the sum of all the squared Fourier coefficients is 1. So Parseval says that 1 is the sum of the squares of all the Fourier coefficients. In particular, that includes all the degree 1 or singleton Fourier coefficients. So that's certainly at least the sum over all I, going from 1 to n, of the singleton Fourier coefficients squared. And these numbers are all the same. They're equal to, f hat 1. So this is n times f hat 1 squared. Okay, and now if we divide by n, it's also equal to n times the influence of 1 on f squared. So if we divide by n and then take the square root, we conclude that the influence of the first coordinate on f is at least 1 over root n. Sorry, at most 1 over root n. Okay, and then we're also done because I could have put in any of the coordinates here. Okay, so that's, again, a combinatorial fact, but it has like that's the slickest proof I know, and it relies heavily on the Fourier formulas. Okay. I'm going to give you one more main definition. Again, with my apologies. Actually, Wednesday's class is going to be the last class that is full of definitions. We'll sort of be done the basic theory by then, and we can start doing more problems. But it's early now, so you have to bear with me. This is a simple definition. You can remember what it is just by its name. The total influence of a function f is just defined to be the sum of its influences. Okay, and we use this notation, boldface I, which on a whiteboard we write like that, of f. It's not the greatest choice, but I didn't choose it. It was chosen by Concali and Lineal, so we have to stick with it. Okay, so that's a quantity. It's easy to compute if you know the influences. But what is the meaning of this quantity? Well, in our favorite case, if f's range is -1, 1, it's also called the average sensitivity. Which means it's equal to the expectation, if everybody votes at random, of the number of pivotal voters. Okay, so everybody votes at random. There's some outcome to the election, maybe 1. And then you look through all the voters and say, if that person in isolation had changed their vote, would that have changed the outcome of the election? And then you count up the number of such swing voters. Okay? This is sometimes called the sensitivity of f on x, which leads to the name average sensitivity. And why is this the same as this? It's because of linearity of expectation. So this is equal to the expectation over x, the sum, I goes from 1 to n, of the indicator, let's say that f of x differs from f of x with the ith coordinate flipped. That's the definition. We can exchange the sum and the expectation. So inside here, we're going to get the expectation of the indicator that f of x differs from f of x with the ith bit flipped, which is just the probability that f of x differs from f of x with the ith bit flipped, which is indeed the sum of the influences. Okay. Let's see. Okay, I'll talk a little bit next time. I'm going to do some more stuff to fill out the class. But next time, I'm also going to talk about the sense in which this kind of measures, if you think of f as the indicator of a subset of plus or minus 1, it kind of measures the size of the boundary of f. Okay? And so we'll eventually see that you can talk about isoparametric inequalities on the Boolean cube in terms of the total influence. But I'll save that for next time. Let me stick to the voting interpretation. So in fact, just to make sure that we're all on the same page, what is the total influence of the parity function on all the bits? N, that's right. Because everybody has influence 1, so you sum them up, you get n. And this is the maximum among Boolean valued functions. Equivalently, for every outcome x, every voter is pivotal. What function has the minimum total influence? That's right. So if I take the total influence of, let's say, the constantly plus 1 function, that's 0. That's the minimum. That's because nobody has any influence. And our other favorite function is the majority function on n coordinates. And what is the total influence there? Nope. It's proportional to root n, yeah. So it's something like a constant times root n, because every voter has influence something like 1 over root n, so you get n times that. Okay, actually, I'm going to save this statement. Because I can just add that if f happens to be monotone, you can use this and get another simple formula. It would also be equal for the total influence. The total influence would be the sum, I goes from 1 to n, of f hat I. Okay. Now, that's a formula well enough. What I'll also tell you, and I guess I'll probably end with this, is that this quantity has a meaning, too, that's nicely related to social choice and the theory of voting. If you have any Boolean function, then this quantity, sum of f hat I, is related to the fraction of voters who agree with the outcome of the election. So let me say what I mean by that. Let f be any voting rule. Then the expectation of the number of voters who agreed with the outcome. Okay, so what I'm saying here is everybody votes. There's a winner, let's say +1, and then you look at all the votes and said, who voted for +1, and count that up. This is directly related to the sum of the degree 1 Fourier coefficients, because it's the expectation over x of the sum, I goes from 1 to n, of, let me write this, a half plus a half xi times f of x. So you see, if xi equals f of x, then this product is +1, and this whole thing is 1. If xi disagrees with f of x, this product is -1, this whole thing is 0. So this whole thing counts up the number of voters who agreed with the outcome. And now we exchange the sum and the expectation, and eventually we get n over 2 plus a half sum I goes from 1 to n, expectation of xi f of x. Okay, and this is by definition, this is f hat I. Okay, so up to this, plus n over 2 and divide by half, this quantity, sum of f hat I, you can think of as the number of people who agreed with the outcome of the election. So back in like the 18th century, this guy Jean-Jacques Rousseau was thinking about democracy, and he said that that's the thing that you should try to maximize if you're holding an election. You want as many people as possible to, like, at the end of the day, say, yes, I agree with the outcome, which makes sense. Okay, so maximizing this whole expression, which is what Rousseau wanted, is the same, of course, as maximizing this, the sum of the f hat i's, which among monotone functions is the same as maximizing the total influence. Okay, and in the last 1 minute, I'll do that. So here's a theorem. Among all functions or voting rules, sum of f hat I 1 to n is maximized by our old friend, the majority function on n voters. Okay, this is if n is odd. If n is even, I leave it to you to look at the proof and find the maximizers. And actually, therefore, you can conclude the influence of f is at most the influence of majority, the total influence, which is about root n, if f is monotone. That's just a consequence of this. And the proof is going to be just a couple of lines long. So let's write out the thing we want to maximize and put in its definition. This is expectation over x. As we saw over in this proof, xi f of x. And now let's do the other thing. Always reverse the sum in an expectation if you can. This is the expectation over x of the sum over I of xi f of x, which let me just slightly adjust. I'll write it as the expectation over x of f of x times x1 plus dot 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 plus xn. Okay, can somebody complete the proof? Why is this? Okay, this is what we're trying to maximize.
It's just the sign of x1 and the maximum value of that for any Boolean function would be the expectation of the absolute value, which is equal to the...
Yeah, exactly right. So imagine x is chosen at random. This is some number. It's either positive or negative. If you got to pick f's value so as to maximize that, you'd always take f's value on x to be the sign of this thing. And in particular, it would be, at most, the absolute value of this thing. But specifically, with equality, if and only if, well, if f of x is the sign of this quantity, which is to say f is majority. Okay, so I'll stop there. And next time we'll talk more about social choice and prove Arrow's theorem.